Well, good morning, everyone. I'm sort of astonished to see such a full hall. I'm really pleased to be here. It's my first time at Devox since COVID started, and that was quite a trial for all of us. So I'm going to talk about kind of a high-level thing about how you do IoT, some of the stuff I've been working on over the last several years, and what most people have done, when they've played around with IoT, it's pretty standard to sort of play around with the Raspberry Pi and think, oh, I've done IoT. But IoT is something that I've worked on for a long time. That's me in, I think, 1971 in front of the ground station for the ISIS-2 satellite. And this is actually one of the photos I was involved in producing. And this is a polar view of the Aurora Borealis, and I did all the software that painted the pixels and did a bunch of the data correction. And so this is kind of where I started out, right, as a code monkey for scientists, and I kind of got addicted to that. It was always just a dramatic amount of fun, when the software that I work on touches the rest of the world. And the landscape for IoT is huge. Over on the left side, there's a Avocado, that's an irrigation controller. Fairly useless device in the Western US these days because there's no water to irrigate with. Then there's a Roomba. And Avocado and Roomba are both AWS clients. Then there's all kinds of medical and factory automation stuff, and then there's weird stuff. So, like on the far left, the guy in the green striped shirt, that's my friend Mark Donner, and that's his thesis project. It's an 8-legged walking robot. The software emulates the neural net of a cockroach. Back at the time, everybody was using giant supercomputers, and a supercomputer of the day had less compute than your cell phone. But nonetheless, Mark's PhD observation was a cockroach has 6 legs, it can walk, it doesn't have a supercomputer. Why is that? So that's what he did. And the one above it, another one of my classmates, Roger Dannenberg, he did that after this one after he graduated. And it's a robotic bagpipe, which some of you might think of with a terrified shudder because it's bagpipes. But it really sounds good. It sounds like a very good bagpipe player, and in fact, because the fingers on it can move much faster than a human, there's bagpipe music that's been composed for this instrument that cannot be played by a human, and it sounds quite cool. This particular setup sat in the lobby of the Scottish Parliament for a couple of years. And it's just bizarre. And there's such a range of stuff as soon as you start touching the world. In most of the sort of enterprise world, you think of the way you touch the outside world is through a web browser. And there are tens of thousands of things on the edge of the network that are functionally similar to web browsers in the sense that they're how you interact with the space outside you. And my gig before I was at Amazon was at a company called Liquid Robotics, and we made these very strange robots that were high endurance, long mission profiles. So a short mission for us was a month, but you could throw one in the water and you just have to scrub the barnacles off of it every year or so. But to be, truly autonomous for months and months at a time, and to be able to do collision avoidance and all kinds of weird data communication and having all kinds of weird sensors on it, that was probably the most fun I've ever had, in my software career. And the fact that I had to go snorkeling for a week a month in Hawaii certainly helped. But it's kind of a worst case for me in terms of a lot of different IoT technologies. And if you ever play with IoT, there's kind of a pattern that most people have, right? They've got some collection of sensors and actuators that they want to coordinate to do something, right? So you write some piece of software that works with the sensor with those, and then you put it on some box, anything from a Raspberry Pi to God knows what. These days there are so many IoT platforms, it's really hard to know. But as soon as you get your IoT app working, all these questions pop into your head like, okay, so how do you go from just kind of goofing around and experimenting to something that you can actually ship in quantity, right? How do you do things like over-the-air update? How do you do things like remote monitoring and remote management? How do you handle fleets of these things, especially when the size of a fleet gets truly gigantic, right? For us, a 7-digit number is kind of the opening bid, right? I mean, one of the things that Amazon does is scale, right? So how do you manage these things at scale? How do you log them at scale? How do you handle the fact that communication is just crap, no matter where you go? And crap communication is entirely normal, right? When you're writing cloud software, a communication failure is a cause for panic, because communication failures don't happen in data centers, and it's just Thursday. If you're in the IoT world. And things like security authentication are even harder because often you don't know if you're behind a firewall, you don't know anything about what's involved in it. Air handling gets crazy. Do you need containers? What kind of containers? I mean, most people, if they talk about containers, they mean Docker containers, but there are also things like Snap and Lambdas and whatever. And network flakiness covers all of these things. And so there are all of these components that end up being part of, what it takes to turn your IoT app into something that can really work at scale. And so we've been building all of these components at AWS. At AWS, we use this phrase, undifferentiated heavy lifting. And for us, that means the stuff that everybody's just got to do because you just got to do it. And some of these are truly, truly sophisticated. Like I could do a whole talk just on over-the-air update, because over-the-air update, when you've got a fleet of millions, where some of them are turned off, some of them are just merely disconnected, some of them are in a cardboard box on a store shelf somewhere. So we've got this layer that we call green grass, which is all about coordinating all of these components, some of which you need, some of which you don't need. The set of these components that we've got is 40 or 50 right now, and we generate new components on a fairly regular basis. So the device side of all this stuff is all open source. It's all Apache 2 licensed, and it's all on GitHub. So there's this old list of the 8 fallacies of distributed computing, and one of the goals of most cloud vendors is to make this list seem true, right? That the network is reliable, that the latency really is zero. Bandwidth is infinite. The network is secure. Topology doesn't change because, with modern magic switches, it's really easy to bend and twist the topology to look like anything you want. And there's, uniform administration. Transport cost is zero. The network is homogeneous. It's all pretty much the same. But, outside of the cloud in the IoT world, pretty much all of these statements are fallacies, right? The network is never reliable. The topology is always changing. You don't know who's administering at any one point because, the path from here to there goes through multiple administrative zones. It's going through, like whoever set up the network in your house to whatever the ISP provider is that you're going through to whatever the backhaul link is, and then finally into the cloud. And the last thing the network is homogeneous. There's lots of different manufacturers, lots of different people managing stuff. And to the greatest extent possible, you actually don't want to have anybody managing this stuff, because the last thing you need is to have some actual human fussing with a box, especially when it's something that you just want to think of as a black box that sits there and does its job. If it's like a utility meter, it's a blob that's nailed to the side of a building, and it never does anything except measure stuff and sends that back to the cloud. And if a human being has to go out and reboot a utility meter, when there's like millions of them around, that would crush anybody. And sort of getting over the problems of the network is probably the biggest thing that people have to worry about, because everything is random. The way that latency changes. If you've got an IoT device that moves around at all, like say you're in a truck and you're driving around, and sometimes you're in Wi-Fi range, sometimes you're in cell phone range, sometimes you're completely out of range of anything. Bandwidth is a variable. Connectivity is a variable. Latency is a variable. They're all variables. And you just have to live with quicksand and smoke. And one of the things that's a part of Greengrass, although it's an optional part, is this thing called the Stream Manager. And the Stream Manager, you can basically pass any kind of bytes over it, but it's usually used for connecting things like anything from video streams to logs to device telemetry. Stream Manager manages a set of streams. Streams have priorities, and it models the bandwidth available on the communication channels that are available, and puts the sort of highest priority messages first. And in fact, for low priority messages, it may just queue them for a very long time. And then there are ways of putting in strategies for, if you're queuing, if you end up with too many messages, how do you let the queues overflow and reclaim the space and stuff like that? So for example, if you are sending telemetry from an engine, you make the sort of regular telemetry like engine temperature, that's pretty low priority. The I'm on fire message is very high priority. So in times of limited bandwidth, the I'm on fire message always goes first. And in fact, the minute by minute metrics like engine temperature, they may just stay on board forever and just be used later on for analysis for like wear and tear. And building all that kind of stuff by hand is pretty much the same for everybody, at least when people do it, right? It's completely common to find IoT devices that have a really hard time with flaky networks, that particularly have a hard time with security. The number of attacks that have been based on security issues is just crazy. So this is one of my favorite pains in the ass. So if you end up having to have like a satellite link in your communication chain, this is some statistics from the Iridium short burst data. And the nice thing about the Iridium network is that their modems are about the size of a cigarette pack, and they're pretty cheap for the modem itself. So people put these on things like shipping containers. You can power them off of a battery, and you can get messages back from anywhere. They're pretty much the only satellite system today that really works in polar regions. But look at the statistics on the chart. At the 50th percentile, packet latency is about 15 seconds. 90th percentile is like 3 minutes or something. But single packet latency of 3 minutes, and it can be much worse, right? So about half an hour to get all of the packets through. And this is an alarmingly good day for Iridium. I used to collect this chart like constantly. This used to be a big part of my life, was looking at that curve. And it gets much worse than half an hour. In fact, there are times when packets can take like a week to get through. And why might it take really long times to get through? Well, one thing is Iridium was designed a long time ago. Their routing algorithms are crap. And they got, when Motorola failed and the original Iridium corporation failed, it got bought out by the US military. So US military packets get like absolute priority. So if there's some like US military operation going on, all of a sudden every packet you send is at the back of the line. It's just crazy. And most of the satellite networks are kind of that way. I mean, Starlink is the first thing that feels to me like a respectable network. But even it is kind of variable. I administer one Starlink downstation at my brother's house, and it is both wonderful and horrible. And kind of the big rule in the IoT space is that your devices must never turn into a brick. And this is sort of a philosophical point that most people in the cloud, because you tend to have like an ops team that looks after like your cloud operations. There's this general sense that what you ought to do is just fail quickly. Just, if things feel wrong, just die and let, the gods above you take care of it, right? And, that might be like some piece of control plane software. It might be like an actual human. I'm sure that all of you have gone in to rescue some broken or misbehaving piece of software in the cloud. But in the world of IoT devices, that's harder to do because, it's a device that's nailed to the side of a building, or it's inside somebody's television set, right? And if you, take a fault in the middle of a logging routine, you don't want to reboot the television in the middle of a World Cup game because violence will ensue. And turning into a brick is kind of the cloud way, because bricks get crushed and recycled, within milliseconds. In the IoT space, they're there, and you just got to soldier on. And so, the way that you think of error handling, so like, I don't know, XKCD to the rescue here, friends. Process negotiate with humans, has encountered an error and was shut down. Close enough. So failure of a system is just not an option. And failure of parts, there's, in the cloud world, there's this sort of saying that something is always failing somewhere. And that holds in the IoT space, but you have to kind of keep going. You have to think about the philosophy of how you handle things that go wrong, how to keep the blast radius of an error. When something goes wrong, how far does that reach? And Java started out as an IoT thing, and a number of the things in Java came out of trying to be as bulletproof as possible. And a lot of it is about things like Java pointers. You really can't forge them. Garbage collection really helps with things like memory leaks. Try catch are completely essential. They all help. And so like this is a code fragment that I like to use this particular construction a lot. Catch throwable. In most people's books, catch throwable or catch any broad any sort of broad exception is just a bad thing. If something unexpected happens, you should just die and let the DevOps people deal with it. But in the IoT world, the systems are never bug-free. There are always unfound bugs that only happen in production. You can test and test and test and test, and there'll always be at least one bug left. Except for a few people I know who insist that they never have bugs, but I usually don't believe them. And so in lots of the sort of best practices Java books, catch throwable is considered an anti-pattern. And for me, the ability to do that was a goal in the design of Java, because even when there are undiscovered bugs, you have to figure out how to soldier on, right? So I tend to build things that are collections of plugins, right? And so you end up with strategies for coping with various kinds of faults, right? And so if you get, in something like this, you fail, and then you can say, well, let's try it again, just because it might be a transient failure. Try it maybe a couple of times, and then maybe we just saw off that plugin and hope that it's a benign one. And oh, by the way, make sure that you log this thing, and keep going, and at least keep, for instance, all the over-the-air update code running, right? The equivalent of somebody, a DevOps person working in the cloud and rebooting things is an over-the-air update, which is usually a moderately complicated operation, and they're in this system they get quite complicated because we allow partial updates, so you can update individual components, and we have like components that cause related components to be notified, and we have hot swappable things. So like MQTT brokers can be hot swapped just because of the way the MQTT protocol works. When you do something like security certificate rotation, some of the services will be able to do that transparently, and some of them require some restarting, and so you can configure how all of those things work. But you can do a lot of updates in complete real time, dynamically, and in a nonstop manner. I mean, there are lots of IoT devices where it's really painful to stop them for any amount of time. So we have customers that are factories, for instance, and in lots of factories they've got an hour a day or so of downtime, but the state where they're the happiest is when they've got so many orders that they can't afford to shut down the factory, and so they want to run the factory 24/7. And if you need to shut things down to do a certificate rotation or any other kind of update, they get really cranky, and so you have to manage all of the hot swappable components that get updated, and sometimes it's not exactly hot swappable, but it's bring in the new service, bring in the new component, warm it up, and then shut down the old one and put the new one in, so that you can do it in milliseconds rather than minutes. And being able to be like really robust in terms of bugs and timing is a pain in the ass. And one of the things that always gets me a little aggravated when talking to folks who, it's pretty common for people to read these, how to program IoT. Take a Raspberry Pi and do this. And if you want to execute a command on a remote device, all the IoT books say SSH to the device and there's a command. But when you've got 10 to the God knows what devices, and some percentage is disconnected, some percentage is in a box in the store, some of them encounter errors during the update because timing, bugs, who knows what. These things make it sort of challenging, right? And typically you have fleets of devices that are sort of partitioned off somehow. Often it's pretty normal to have like a fleet of meters that are like a whole country. And then you've got a sub-fleet, which is the ones that are close to maintenance depots, so that if something goes wrong, it's easy to go kick them. And then there's like a testing fleet that sits in the lab, and then there's like a device that's sitting on a developer's desk. And so you need to be able to do, subsets of the set of all the devices. And you need to be able to do phased rollouts in some of these things. So that if you've got, a few million devices, typically you will test the crap out of an update. But still, things leak through that errors that you didn't find in testing. So it's pretty typical to want to be able to do phased rollouts. And by that, what I mean is, you do like 5% of the fleet every hour, and or you do some kind of an exponential thing for you. You'll first do 1% of the fleet, then 2% of the fleet, and then 4% of the fleet, then 8%, and you keep doubling until it's all done. But as you roll it out, you collect gobs of statistics on what went on, and you'll stare like mad at all the errors, and decide whether or not those were transients because it's a device that physically has a fault, or has some strange configuration or whatever. But sometimes you can find a deployment problem partway through a rollout, and then you want to roll them back if you discover that there's a bug that hadn't shown up in testing. So you have to be able. So that means not only do you need to be able to collect statistics as you roll out, but you also have to be able to roll back, and rolling back is complex. And also, for most devices, there are times when it's a bad idea to do an update, right? So if you've got like a robotic arm that's doing something, you can't switch software, in mid-motion. You can't update software in a television set in the middle of somebody, watching a World Cup game. And so there needs to be a bit of a negotiation between the over-the-air update software and the software being updated, to say, is this a good time? Should I wait? And there also needs to be a way to say, I don't care what that device says, it's broken, just do the update, no matter what it says, right? Because there can be a bug in the is it a good time software, and it all too often happens. And after a while, you've got a fleet of devices that are all slightly incompatible because they're different chip generations, they're different hardware generations, different sensor generations. When you have these heterogeneous fleets, which are essentially the rule, when you first launch a product, it'll be a homogeneous fleet, but within a year it'll be quite a mixture and a real pain to deal with. And so the automated recovery and compatibility management, and a bunch of that is one of the reasons why the core part of this stuff is in Java. We do exactly one build, and by the amazing modern JVMs are available on pretty much everything. Even some of the weirder versions of Linux, like Yocto. Yocto is a wonderful system, but it is a little touchy. And, when it comes to, asking for status of things, being able to get the status of a dead system or an unplugged system or a system that is still in a cardboard box in the store shelf, you need to be able to ask those questions and get an answer so that you can actually have a dashboard that says, "Bleh." It's not always the case that a system like Linux will work. Sometimes, the real-time operating systems really matter. And again, I don't know if you can I guess that's pretty reasonable, but, offloading, automated cars onto humans is just not going to work. You have to do these things in real time. You can't have any kind of reasonable delay. And sometimes, one of the things that I find particularly interesting is how AI is often a form of data compression, right? So it's completely normal to attach a camera to an IoT device, run an ML recognizer on the device, and then turn a video stream into an event stream, right? So that instead of doing the video analysis on the cloud, you do the video analysis in the device, and you just send events that says parking spot 37 is empty, or parking spot 37 is no longer empty, and that particular example of telling what parking spots are empty and not empty turns out to be a big business for a couple of companies. And there are also companies that tend to have parking meters, where the parking meters emit events, so that they can, send a traffic officer, as soon as the meter expires and there's a car in that spot, a traffic citation officer will come out and ticket you if you happen to be in the wrong jurisdiction. Right? They'll get you, and it's a little tragic that is a killer app for some people, but it really is. So here's a little video I did for some folks to get them to understand why timing is a big deal. So these are the curves for the two motors, right? So that's kind of how you have to coordinate a hand to draw a circle. So this is the signals are correct, but their clock skew is a little wrong. This is one where the two motors have clocks that are slightly different rates, and it's not drawing a circle. This is one where there's a latency spike in the controller for one motor, and you can get that kind of stuff. And then when there's a little bit of noise. And this one I think is particularly interesting because if you look at the traces, a human looking at that trace will think, those are small errors. But, when you sort of multiply errors, how many people here have taken a numerical analysis course? That's not enough people. I always hated numerical analysis. I took a lot of numerical analysis courses because I had to. I would have never voluntarily taken a numerical analysis course, but man, it saved my ass so many times. And just the way that, small errors here and small errors there, mix them together and you get much larger errors. Although sometimes, if you're lucky, they're much smaller errors, and understanding which cases are which is an important deal. But nonetheless, when the quality of the operating system and the network, because sometimes these motors have separate control processors and they have separate, they're connected on a network, and believe it or not, there are actually real-time network protocols that are complicated, expensive, but they actually work. So testing. So the testing in the IoT world is somewhat more complicated than it is in the cloud world. Often people will actually take systems under test and make them go live, and then just sort of claw them back and have a few customers have bad experiences. But there's kind of a hierarchy of testing that everybody does, right? There's unit testing that goes, eventually, into the real world. But with IoT testing, because there's an actual device out there, right? You do unit testing. You try testing all of your software in simulations. Then you do bench testing of components, and then you start testing it on the real device. And then if this is like an autonomous vehicle, you have to test it in some test range that you probably have. In my previous job, we had a license to do testing on about 50 square kilometers off the coast of Kona. And then you go and you run things in the real world, and you hope that when you're in reality that no new bugs show up, but some will. So this particular little video that I showed was from my previous job, and that this is a trace of taking two robots, restricting them to a square kilometer, giving them random routes, and that will occasionally cause collisions, and then you make sure that the collision avoidance software actually works. So this is that was just collision avoidance software being tested in a test range. And sometimes testing is really extreme. I mean, the people who do things like airplanes or medical devices. I mean, so this is a Da Vinci surgical robot. If you ever have to have like prostate surgery, this is a pretty common way to do it. And I have no idea how these guys test. How do you, that's your mother on the table. I would freak out. There was a friend of mine who worked for a company that did flight control software, and back in the day when they were doing this, their employer had this policy that if a test pilot bought it, then they would do an analysis to figure out where the software bug was, and then the engineers responsible for causing that had to explain it to the family. And it's like, really? It seems a little sick to me. But it keeps the pressure on you. So this is a little bit about the AWS device platform. So we've got kind of two platforms. On the small end of things, if you're doing firmware for a light bulb, there's this thing called FreeRTOS. It's MIT licensed. It's on GitHub. It's easy to find, and its sweet spot is anything that's like too small to run Linux. And for anything that's big enough to run Linux, that's from like a low-end Raspberry Pi up. That's kind of where Greengrass runs. And so it runs on every flavor of Linux. So it's, Red Hat, Ubuntu, Debian, Yocto, and it even runs on Windows. Does not yet run on Android. Android is definitively weird. We've been trying Android for a while, and man, is it weird. But, yeah. Anyway, thanks. I think I've got 5 minutes left for questions. I don't know how you want to, right there?
So what's your preference? Would you like OSGI or Docker for IoT devices?
So the question was about, do I prefer OSGI or Docker? Actually, I don't prefer either of them. I tend to just write code and run it without a container. If only because, Docker can be quite large. And if you're using a version of Linux like Yocto, you're counting the bytes sort of pretty closely, and the space taken up by Docker is a little much. And Docker is particularly a problem because it's trying to insulate you from the device it's inside. And you can do, there's all these kinds of Docker facilities for like linking between, say, a USB serial line and the code inside the Docker container. But if you don't use a container, then it's fine. A Linux process is itself a container. So there's a fair amount of insulation there. And yeah, it works out pretty well to not do any of those. But sometimes people like to have Docker containers because it's then easier to do certain forms of testing. And then you just have the same thing that you run inside testing. And I personally don't care. It's kind of hard to find people who are using OSGI containers in IoT. It's pretty common to find Docker containers. But most of the stuff I've seen people doing they just write code. Other questions? Yep.
Did you ever build a funny or weird IoT device yourself?
Do a funny or weird?
Did you ever build something like the headlines or anything funny or weird yourself, an IoT device, because you have the knowledge?
I did something that controlled a puppet. It was actually I had bought a puppet of in Prague. They're really into puppets in the Czech Republic, and so I just whipped together a bunch of servos and made the puppet dance. But it's easy to do that kind of stuff. The things that are available to build that, there's a company that makes like servo controllers that plug into USB, right? And the kind of I2C bus stuff that's kind of the standard practice on a Raspberry Pi. That tends to be a pain in the ass because it's really easy to electrically fry your system, whereas the servo board connectors that use USB, okay, they cost an extra $2 or $3, but you're not going to fry the processor or anything else. And there's like a long list of things over the years. But other questions? There must be one more. I'm not seeing any hands, so oh, where? There.
I was wondering if GraalVM native image is making Java more relevant to your work on these devices.
Could you say that louder?
If I was wondering if GraalVM native image and all of that when you heard at the conference is making Java more relevant on the devices you're working with.
So there are things that we can do. So the question was, are there things we're doing to make Java more relevant on devices? We do a lot to make it easier to use on devices. If you look on like the Corretto distributions, we build Corretto for all kinds of platforms. And surprisingly, a bunch of platforms that are not found inside the Amazon cloud, and that's entirely for the IoT world. We even provide things like Yocto recipes so that you can build a Yocto install. These days there's no JRE anymore because you just use JPackage for that, and we've done some to try to make that a little easier for people to use, although the JPackage system itself is pretty good. It still feels like the biggest. In some sense, I find the enterprise use of Java to be the biggest problem with Java on devices, because people have it sort of in their mind that it's a cloud thing. But in fact, it works beautifully, and especially with the modern JVMs. So later this afternoon, Kelvin Nilsson is going to be doing a talk on garbage collectors. And modern garbage collectors are amazing. And one of the things one of the properties of garbage collectors that's really relevant is maximum pause time. So these days it's way below a second. And it can run with much less overhead, right? So back in the days of JDK8, it was common to over-provision heap sizes by a lot. And that was a real problem in the IoT world. And it's not an issue these days. People, I always tell people to use at least JDK 17. It's the most modern LTS release, but Greengrass runs on everything from JDK 8 to JDK, you can get 19, I forget which is the latest one. They come out just too fast. And so we test on all of them. I mostly run, in my work on 17. But it works really well these days. And actually the biggest challenge for Java on IoT devices tends to be space. And we did a big analysis of the space problem, and discovered that the big issue was not Java itself, was not the garbage collection anymore. It was entirely libraries. So many, for example, so many libraries have their own complete HTTP stack. And on systems with gigabytes of RAM, that's not a big deal. But on an IoT device, it's really easy to find that you've got 4 or 5 HTTP stacks, all in use on an if your IoT app gets it all complicated, you touch something from Apache Commons, you get the Apache HTTP stack. You touch the Amazon SDK and you get the Amazon HTTP stack, and then there's the Google HTTP stack, and there's several others. And pretty soon you found that for every library, there's an HTTP stack, and you end up with some uncountable number of JSON encoders and decoders. Sometimes people are really good about it and say, well, I might be running in a small memory system, so I'll just use Jackson Jr. But then you'll find that some library you pulled in, they care about performance more, so they've used full up Jackson. And then it's like, okay, so why did I bother with Jackson Jr.? Because, the big one is loaded. But sometimes it sort of goes the other way, because if you really, if you're building an IoT device that needs extreme network bandwidth, Java does that really well. Anyway, I'm now way over time, so thank you.